Hello, everyone. Welcome. Let us start today's lecture. So last time we were talking about reducibility, and today we will not talk about reducibility much because whatever that we had to cover has already been covered, and everything else that is required for us to cover, we will cover during this chapter on time complexity. So today we are starting a new chapter called time complexity, and this chapter is where we would be interested in knowing exactly that what happens when we do some computation. Okay, is that clear? Okay, so previously we have been talking about computability. Okay, so what do we mean by computability? Computability means that what is computable, what is not computable, and after that we actually talked about. So basically, there was one important question which was about decidability, right? So we were interested in knowing if a language is decidable or not decidable, right? And that led us to some important theorems, and we found that there are some languages which are called decidable, there are some languages which are undecidable, and then there are again some languages which are not even Turing recognizable. So this actually draws or gives us a picture about the entire computability, and I think we drew a picture as well that we have at the heart of this picture is the regular languages, and then afterwards we have context-free languages. It's better if I write CFGs. Okay, and after CFL, we have something which is decidable. Then we have recognizable. So this is Turing decidable, Turing recognizable. And then there's outside, right? So this outside space, which is outside all these ellipses or circles or spheres or whatever you want to call it, is outside. So right now we are not interested in knowing that what is inside these things. What we are interested right now is that, okay, we know that we have something which is computable. Now we are interested in knowing that how efficiently we can compute it. So most of the time we would be talking about efficiency. Okay. So over here in this course, when we talk about time complexity, we only talk about time complexity from a very different point of view than we do exactly the same thing in the analysis of algorithms. So when you talk about analysis of algorithms course, we are more interested in actually implementing the algorithms and then figuring out that what is the best algorithm for doing what. Right now, we will be talking about the problems and we will be talking about the complexity of solutions rather than typical or particular problem, right? So anyway, so let us start. Any questions before we begin?
सर हम reducibility skip कर रहे हैं क्या?
नहीं, I think you missed the part. We are not skipping. We already have covered a lot of things, and whatever that is not covered will be covered in some way in complexity.
अच्छा, क्योंकि हमने पिछली क्लास में हमारी स्टार्ट किया था, हमने कुछ पढ़ा नहीं था इसके अंदर।
हमने पढ़े थे 2-3 theorems.
हाँ सर, सही सही।
Right. Okay, so let's begin. Imagine I give you a simple problem, and I'm taking these problems from the book, so you don't have to. I mean, you just see what we are doing. Suppose I have a language A that is defined as k zeros and k ones, okay, such that k is greater than equal to 0. That is non-negative. So the first question, is A decidable? Yes or no? Is A
I think
decidable?
did we do this like in
What?
the first class of Turing machine?
Mm-hmm. So is this
So is
decidable
this
or no? Yes or no?
I
Yes, sir.
think it is decidable.
It is decidable. Okay. So when you say something is decidable, what does it mean?
The Turing machine should be able to return a yes or no answer.
Exactly. So this is decidable because we can construct a Turing machine that if you give any string of 0 and 1, it will tell if that 0, 1 string is in this language or if it is not in this language, right? So you can construct a Turing machine, you can construct a function Java and C, C++, or you can create an algorithm, or you can write a program, and so on and so forth, right? So it is possible for us to answer this question that given any string x, which is a string over alphabet sigma star, where sigma is equal to 0 and 1, we can figure out if x belongs to the language A or x does not belong to language A, right? So we can answer this question, so it is decidable. So decidability is out of the question right now. So we are not talking about whether this language is decidable or not. We know this is decidable. Now the next question is which TM decides A? Can you construct a Turing machine which decides A? Can you construct a Turing machine that decides this particular language A? Can you do that?
Yes.
Okay, how would you do that?
For every zero you cross off, go to the right and cross off one. And when you're done crossing off all the zeros, check if there are any ones left.
Okay. So it means that it is possible because we know that it's decidable, so you can construct a Turing machine, right? And is it possible that, I mean, is it true that there are multiple possible solutions to solve this problem? That is, there are multiple possible Turing machines which will do exactly the same thing.
Yes.
Okay. So it means that it is also possible that if I give this question in an exam and I ask you to construct a Turing machine that decides this language A, imagine there are 100, almost 100 students in the class, 90 plus students in the class, then I hope that there will be multiple different solutions, not necessarily 90 different solutions, maybe 4 or 5 different solutions which would achieve the same task, but not necessarily in exactly the same sequence or style, but will achieve the same task, right? So they would be correct, and they will do exactly the same thing, that those Turing machines will actually decide the language A, but not necessarily in the same style and manner and the way, right? Right. So the question arises, and that question is, if I give a string x of size n. So if I say that the size of the string x is n, that is the number of elements in my string x is n, okay? And I have multiple different Turing machines. For example, I have a Turing machine M1, I have a Turing machine M2, and I have a Turing machine M3, and many more Turing machines. And all of these Turing machines correctly decide the language A. If I pass this string x to all of these Turing machines, one by one or simultaneously or whatever fashion, since all these Turing machines are implemented in different way, do you think the number of steps required to achieve or arrive at the answer, whether that string x belongs to the language or x does not belong to the language, will be same in all three or all Turing machines or not?
It will be the same.
It will be the same. Are you sure?
So I think it would be unreasonable to assume it will be same in all of them.
Okay, why it is unreasonable?
If there's so many steps that you can do it in, I think it's
Mhm.
unreasonable to assume that all of them will be able to do it in the exact same like amount of steps, assuming
Exactly.
there's multiple ways to do it.
Exactly. So if there are multiple ways, so I think let me open the chat as well. So if there are multiple possible different solutions, different possible Turing machines which achieve the same task, and they are all correct, then it is possible that some of these Turing machines will do the same task in fewer number of steps than the other. Okay. And if the number of steps required by all Turing machines are different, because these Turing machines are different. So if you have a set that contains different numbers, then if the set is finite, then there must be a minimum element, right? So every finite set of numbers with some order contains a minimum element, discrete maths, if you remember. So if it contains a minimum number, then there must exist a Turing machine which achieves this task with the minimum number of possible steps, right? Right or wrong?
Yeah, yes.
Okay, so for example, machine M1 takes, let's say, n steps. M2 takes n plus 1 steps. M3 takes m minus 5 steps. M4 takes, let's say, n minus 2 steps, and so on and so forth. Every machine takes some steps to resolve this question, whether X is in the language or X is not in the language. And now we know that once it arrives at the conclusion, arrives at the solution, we just count the number of steps. And I haven't yet defined what is the number of steps. I will define the number of steps later on. But imagine we have some vague understanding of what do we mean by number of steps. Then we know that the number of steps are different in some of these Turing machines, right? Some of the Turing machines will do in the same number of steps, but some others will do in different, and some will do in less, some will do it in more, and so on and so forth. So if I arrange all of these Turing machines according to the number of steps they take, I can find out a Turing machine which does the same task in the fewer number of steps, right? And then I can say that this is the Turing machine which is most efficient in the set of the entire Turing machines which solve this problem, which you have come up with. Okay. And this is what we mean by measuring the time complexity. Okay? I haven't defined so many things here, and I will define all of them one by one. What I just wanted to make sure that what we understand from this construction is that whenever we have some decidable problem, so forget about if some problem is decidable or not decidable. Imagine a problem is decidable. So if this problem is decidable, it means that we can construct a computer program. We can construct a Java function. We can construct a Turing machine, which correctly decides the language, right? And now we are only talking about the problems in terms of languages, right? And you also remember that every problem, every computational problem can be converted and encoded into a form which we call the language problem, right? That is the membership query problem. So we all know that. So it means that we are only talking about the problems which are decidable. And once we have a decidable problem, we are now trying to see that among the class of solutions, among the collection of Turing machines that we can have, which is the better Turing machine to solve this problem, or which is the best Turing machine to solve this problem. And that's exactly what we will be doing in this chapter, which is talking about time complexity, right? So this chapter talks about time. We haven't yet talked about time, but I think you understand from whatever that we have done so far from the construction that what we are going to do. Okay? If you understand that, fine. Otherwise, I will try to resolve those doubts, and then I will explain that what do we mean by time, what do we mean by complexity, what do we mean by measuring, and how do we do it for all kinds of Turing machines. Any questions before I?
No, sir.
Okay. So suppose you write a program, okay? And you write the program in your favorite language, and imagine that program is a program that whenever it is given a sequence of numbers, an array of numbers, it sorts this array in ascending order, right? And from the understanding of data structures and algorithms from last year especially, you know that there are multiple ways to sort a given array of numbers, right? There's double sort, there's insertion sort, there's selection sort, there's quick sort, there's merge sort, there's heap sort, and there are many other sorting algorithms. And you know that some of these sorting algorithms are fast, some are very fast, some are slow, some are extremely slow, right? So when we talk about sorting, we know that the sorting is a decidable problem, right? Why sorting is a decidable problem?
Because it has a finite set that you have to sort through. That's why it's decidable.
No. So the thing is that when I say that sorting is a decidable problem, it's basically misusing the terminology for decidability and the problems. So first of all, whenever you talk about algorithms, the understanding of problem is slightly different than when we talk about automata theory and complexity, right? So there are two kinds of problems that we will be dealing with, okay? The first kind of problem is called optimization problem. Okay. The second kind of problems are called decision problem. This is a basic classification of problems into what kind of problems that we are trying to solve, okay? The optimization problems are those problems which solve something. For example, given an array of numbers, sort this array of numbers is an optimization problem, right? For example, sorting is an optimization problem. Okay, searching is an optimization problem. Okay, and there are many other problems that you have seen so far in your computer science studies at IBA and before, which are optimization problems. Optimization problems are basically those problems in which you are given some input and you are expecting an answer. For example, if I give you two numbers and I ask you to add these two numbers and give me the sum of these two numbers, it is an optimization problem. If I give you a sequence of numbers and I ask you to multiply all these numbers, this is an optimization problem, right? So an optimization problem is a kind of problem in which the answer is not just yes and no. The answer is more complicated than yes and no. The answer is something which is a number, or it is a sequence, or it's an array, or it's a graph, or it's a path, or it's something else, right? For example, if I tell you that given a graph, okay, find the minimum spanning tree. Finding minimum spanning tree is an optimization problem. First of all, the answer to this question is a spanning tree. For example, given this graph, I can say that this is the minimum spanning tree. Okay, this could be the minimum spanning tree. So if this is the minimum spanning tree, fine. How do we define minimum spanning tree? Minimum spanning tree is defined in terms of if I add the weights along all the edges, for example, in this particular case, I can say this edge has cost 2, this is 3, and this is 2, this is 3, and this is 4, this is 7, this is 9, this is 10. Now, definitely, this is going to be the minimum spanning tree because the sum of these edges is the smallest possible sum, right? And I have preserved all the vertices of the graph, and the resulting graph is basically a tree, okay? And I've not deleted any vertex. I have deleted some edges, but not the vertex. So this is a tree, definitely a tree. Now, I also claim that the minimum spanning tree because I know how to prove that how this minimum spanning tree algorithm works. So this is an output of an algorithm which could be a Prim's algorithm or clustering, right? So optimization problems are all those problems in which the answer or the solution is not just yes, no, accept, reject, but it is something. It is either a graph or a number or an array or a string or something. Okay. So this is called an optimization problem. And why they are called optimization problem? Because we are finding a solution from a set of possible solutions, and we find the best solution from the set of possible solutions, and we say this is the best. So this is the optimal solution. So they are called optimization problems. So sorting is an optimization problem because given a sequence or an array of numbers, sorting requires you to arrange these numbers in such a way that you have some order. You impose an order. Most of the time, the order is like ascending order or descending order. But whatever order that you are going with, there is a particular order. It's not just random shuffling or jumbled order. It's just an order in which you know that the first element is less than the second element is less than equal to third element is less than equal to fourth element, and so on. This is an ascending order. So among all possible arrangements, you find an arrangement in which this is the property, and then you output it. So sorting is an optimization problem. Now, on the other hand, decision problems are those problems where the answer of a question is yes or no, true or false, accept or reject, right? So we have a Boolean answer in decision problems, while optimization problems have huge variety of possible answers, right? So for example, I can always convert these optimization problems kind of thing in decision problems as well. How? So I can say that my sorting is also a decision problem. How it is a decision problem? For example, I say that I have a set X which contains numbers, not a set. I have a sequence X which contains numbers as 1, 5, 6, 9, 10, and 12. And my question is X sorted? Is X sorted? And by sorted, I mean ascending order. Is it sorted in ascending order?
Yes.
So every such question will be either answered as yes or no. Okay. And what is the property of decision problems? They have binary output. So this means that this question, which asks whether a given sequence is sorted, has two possible answers. Either this will be yes or it will be no. If the list or the array is sorted, I would say yes. If the list or the array is not sorted, I would say no. For example, if I say that Y is a sequence which contains 3 and 2 and 9 and 0, and the question is Y sorted? The answer is no. It is not sorted, right? So it means that if I encode this sorting problem in such particular way, then sorting problem becomes a decision problem. Okay. So when we talk about automata theory and when we talk about complexity inside automata theory, we are only interested in decision problems. Okay. We are not interested in optimization problems. We are only interested in decision problems. Later on, we will see that there are some relaxations, and we will also include optimization problems in certain applications and certain understanding. But if I don't mention it, if I say that there's a problem A, a problem B, a problem C, a problem X, problem Y, then all those problems A, B, C, X, Y are decision problems. And when a problem is a decision problem, the answer of a problem is either yes, no, or accept, reject, or true, false, or 0, 1, right? So 0 can mean false, reject, and 1 can mean accept and true. Clear?
Yes,
Clear?
sir.
Yes,
Okay. And we can also convert this decision problems into language problems as well, right? For example, I can create this set sorted, and I can say that this sorted list contains all those sets X or all those sequences X such that X is a sorted sequence. Okay, X is a sorted sequence. This is my language. Now I say that given some X, okay, and over here the sigma could be all possible things from 0 to 9. So I have all possible numbers here. So I can say that given an X over, just a second, given an X over this sigma star, does X belong to sorted or not? So the answer would be yes or no. When I say the answer is yes, it means that X is sorted. And when the answer says no, it means X is not sorted. And we have seen such problems before when you talked about decidability. So it means that we are basically encoding a problem, right? So we are encoding the sequence of numbers, right? So it means that we cannot simply just use those problems. We can also make these problems into language problems. So, and when we talk about language problem, so this problem is basically, this decision problem becomes a membership query problem. Okay, so this problem becomes a membership query problem, and a membership query problem means that we will be given some strings. So now you can consider this X as a string, and this string, whether this string belongs to the language sorted or not, right? So again, now the entire understanding that we have developed from DFAs, NFAs, and Turing machines and context-free languages, we can apply it here. We said that now we have a machine which we will call a Turing machine, which we call a Turing machine for sorted. So let's call it Turing machine T for this sorted. This will receive an X string, which is from the sigma star, and it will answer yes or no. When it says yes, it means accept. When it says no, it means reject, or whatever that way you want to go. When it says it rejects, you mean no. When it accepts, you mean yes, or when it says yes, you means accept. Is this thing clear?
Yes.
Okay. So now we have now we have some basic understanding of what kind of problems we will be looking at. So we will be looking at problems which are decision problems, and we have a basic understanding that these problems are basically defined in terms or formatted in terms of a language problem, right? Now, if they are language problem, we would assume, because in this chapter, we are not asking whether a language is decidable or not. So the only question that we are asking right now is not about decidable, right? So we know that these languages are decidable. If they are decidable, it means that we can construct a Turing machine. And if we can construct a Turing machine, we know that the Turing machine would be a decidable Turing machine. It's a decider. So if it is decider, it means that it can solve the membership query for that particular language. Well, it can answer. It will stop on all possible inputs. It may take a little bit more time for some input string than others, but it will eventually stop, right? Okay.
Yes.
So let me write one simple definition which we would use in this chapter. Okay. So we said that let M be a deterministic Turing machine. In fact, when I say Turing machine, by default it means deterministic, right? Unless I say it is non-deterministic. So let M be a Turing machine, and usually when I say M means deterministic, N means non-deterministic, right? So let M be a deterministic Turing machine, or M be a Turing machine that halts on all inputs. What does it mean? It means that whatever this Turing machine is, it is basically a decider. Okay, it's a Turing machine which decides some language. Okay, so we define a term which we call running time, or time complexity. time complexity of M, which is the Turing machine, is the function. Okay, what function? The function f, which is from the set of natural numbers to set of natural numbers. Okay, where f of n is the maximum number of steps, okay, that n uses on any input of length n. Okay, if f of n is the running time of m, we say m runs in time f of n. Okay, and m is n f of n time Turing machine. Okay, so this is a definition which is slightly long definition, but it contains a lot of information. So I just wrote this definition, so let me explain what do we mean by it. So suppose I have a deterministic Turing machine. So deterministic Turing machine means that it is not non-deterministic. There is only one flow of the execution, and it's a linear kind of thing, that the transition function of the Turing machine is deterministic, and after every transition we know exactly the state of the machine, or in state means configuration of the machine, so we know exactly what is the configuration. So I know that every state, every possible configuration will lead to one possible configuration, right? So we cannot have a Turing machine which is at the multiple different configuration at the same time. So we know the path of the execution. There's only single path of execution. So we say that if M is such a Turing machine, such a deterministic Turing machine, and furthermore, we say that it halts on all possible input, it means that whatever Turing machine is doing over here, the language of the Turing machine is a decidable language. That's exactly what it means by halt. And whatever string that is in the language, it will say accept. Whatever string that is not in the language, it will say reject. So it halts, it stops its work on all possible input, right? So far, so good. So we have a deterministic Turing machine which decides some language. So this Turing machine is a decider. We say that the running time or the time complexity of this Turing machine is basically a mathematical function. Okay, and that function is between that. Let's call that function f. That function f is basically from the set of natural numbers to the set of natural numbers. Okay, and it will become clear that why we have set of natural numbers here. And sometimes later on we may see real numbers somewhere, but right now natural numbers are enough. So we say that this function f is a function from natural numbers to natural numbers. That is, the input of this function is a natural number, the output of this function is a natural number, and this function is called the time complexity or the running time of the Turing machine. Okay, so what does it mean? What does this function do? This function is basically a function that gives us the maximum number of steps that this machine M uses on any input of length n. Okay, this is very important to understand. So if I have a Turing machine M, which is the deterministic Turing machine that stops on all possible input, this Turing machine will take some strings as the input. Some of these strings will be termed as accepted. Some of these strings will be termed as rejected. Now, suppose when I input some string x, okay, if I input some string x of length n, okay, so I can find out what is the length of the input. The length of the input could be 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be any natural number, right? That's why we have natural number as the input. So we cannot have an input of half or input of 3/4, right? So it is impossible. So either we will have a string of 0 length or length 1 or length 2 or length 3 or length 100 or length 1 million or something like that, right? So whatever that the input, the length of the input is, that is basically the size of the input. Okay, we call it the size or the length of the input. Now, for that input, Turing machine will do something, right? So we know, we have already seen that how Turing machines work. So how do they work? The input is taken by the machine, then machine starts reading one character at a time, and depending on the transition function, it decides what to do, right? Whether to go into some configuration C1 or the other configuration C2 or whatever. Whatever configuration is it goes, that configuration depends that what character it is reading right now and how the transition function is defined for that particular language. But whatever is the case, since we know this machine halts on all possible input, we know that after some finite number of steps, this machine will stop. And when the machine stops, we know that the machine stops, our Turing machine stops, whenever it goes to the accept state or the reject state. If it goes to the accept state, we will accept the string. If it goes to the reject state, we will reject the string. But it will eventually halt in finite number of steps. Now, at that time, we would just calculate, we will just add all the number of steps that it took. When it reads the first, it's a step number 1. Then after reading the first character, it goes into another configuration. And at that configuration, it does something and then goes to another configuration. So if I just take out all the possible configuration that it went in, since it's a deterministic Turing machine, then I know that there is only one sequence of configuration, right? So there is only one sequence of configuration. So imagine I have this Turing machine M, and this M receives some X. So this X will say accept, or it will say reject. We do not know what it will say, but whatever it is the case, so what happens is this X will make Turing machine. So this is configuration number 0. That is the starting configuration. This starting configuration will go into some configuration C1, then it will go to C2, then it will go to C3, and so on and so forth. Okay, and it may go to some CK. And at this point, it will either accept or reject. Okay, this will either accept or reject. Now, what is this length of this configuration? We just count how many steps are there. So this is step 1, step 2, step 3, step 4, and so on till step K. So it took K steps, in this particular case, K steps to accept, reject X. Okay? But at the same time, you have to be careful about the length of the string X. The length of the string X is N. It is possible that in this particular string X, it took K steps. If I send another string of the same length, it may take more than K steps or less than K steps, right? Right? So we say that this function f, which I defined over here, this function. So this function f basically measures or counts the maximum number of steps that this machine M takes on any input of length n. Okay, any input of length n. So f of n is the maximum number of steps by n on any input of length n. Any input of length n. Do you get it?
Yes, sir.
And since this function is representing the number of steps, so the number of steps would be either 0 or 1 or 2 or 3 or 4 or 10 or 100 or 175 or 325 or something like that, right? It can never be 1.3. or 73.2 or something like that, right? So it would be an integer, and not only integer, but a natural number, right? It cannot be negative, it cannot be fractional, it cannot be real. It would be a natural number, right? So we would see that a Turing machine takes no steps, or it can take 1 step, or 2 steps, or 3 steps, or 10 steps, or 325,633, right? Or whatever. So whatever the number of steps, it would be a finite number and finite integer, positive integer.
सर
Okay.
सॉर्टिंग एल्गोरिथम में मैक्सिमम नंबर ऑफ स्टेप्स कैसे होते हैं अभी?
We will go to that point. Don't go ahead of yourself. That's all. Okay, we will
Sir?
figure it out. Yes.
Sir, so just to clarify, so basically what we're trying to find is within a Turing machine, what's the maximum number of configurations a Turing machine has gone through to accept or reject an X?
Exactly.
That's basic. Okay.
Yeah. So the number of, it's not the number of configuration which is important. Number of configuration, number of configuration tells us the number of steps, right? Since it is a deterministic Turing machine, so the sequence of configuration is basically the number of steps, right? When it goes from configuration I to I plus 1, this means it took 1 step, right? So if it went to K configurations, अच्छा ये K जो configuration है जरूरी नहीं कि सारी distinct हो. We are just writing all of them. So we can say that it went from C0 to C1 to C2, then it went to C3, then it went to C1, and then it went to C4, and then C6, and so on and so forth, right? Suppose it stopped here. तो अब हम क्या करेंगे? हम चेक करेंगे कितने स्टेप्स लिए इसने. 1, 2, 3, 4, 5 और 6. So it took 6 steps. Okay. Even
Yes,
though
sir.
C1 is repeated, doesn't matter. Okay, it doesn't matter. So what we are interested in, कि कितने steps लिए. एक step क्या होता है कि when it goes from one configuration to other, or in other words, we can say the number of times we used the transition function. Okay, so every application of transition function means 1 step. पहली दफा ट्रांजिशन फंक्शन अप्लाई किया 1 स्टेप, दूसरी दफा किया 2 स्टेप, तीसरी दफा किया 3 steps, and so on. Clear? Okay. So the important question is why we are associating the word time with the number of steps. So it is important to note here, or it is important to understand that the time is basically something that we cannot measure when you talk about computers. For example, I give you a problem to solve in Java, and all of you write a program that does something. Okay? And you implement it, and you execute it, and you measure the time. For example, you say that I give an input of size, let's say 100. 100 means an array of size 100 is given as the input, and so on. And you measure the time in seconds or microseconds or whatever, right? But the problem is that the program that you have written is not something that you are going to implement and run today and tomorrow, and that's it, and you will forget about it. If you write a program today, it is possible that you may execute this program tomorrow, or day after tomorrow, or 5 years from now, or 20 years from now, or 30 years from now. And if I look back in the history, I know that every year the performance of average computer increases. So for example, in my time, when I started doing undergrad and before that, computers used to be very slow. I remember the first computer that I bought was very, very, very slow. It only had 2 megabytes of RAM. Okay, 2 megabytes, which is much less than an average iPhone photo, right? So just 2 megabytes of RAM. So everything was inside that 2 megabytes. So the entire operating system, when I would load it, would run, would occupy some space in it. And every application program that I would load would also be there, and the compiler would be there, and so on. So everything was within 2 megabytes. And the performance was also very slow. So for example, if I would write a code, it will take very long time to execute it. Now, if I compare that time with now, 2 megabytes is nothing, right? So, but now we have computers with 16 gigabytes of RAM as the normal computer. And we have even computers which sit on our desktops, which have much more than that RAM. For example, 128 GB or 512 GB or 1 terabyte of RAM. So you should not be surprised that there are computers with terabytes of RAM. In fact, I had access to a machine with that which had 1.5 terabytes of RAM. RAM, not hard drive, RAM. So we know that RAM is increasing, the performance is increasing. At my time when I started, there were very small, simple processors which could do only one task at a time. Now we have computers in which we have 4 and 5 and sometimes 6 and 8 different physical processors present on the motherboard. Each processor with internal division of like 4 or 8 cores, and each core with multiple threads. So you can imagine the time that we could save on those machines, right? So today's computers are much faster than the computers of past. And the computers which I used as when I was a student was much faster than the computers which were there in 1950s and 60s, right? And 70s. So we know, if you look back, the computers are becoming very fast, very rapidly. So if I write a program, a complicated program today, and measure the time it takes to solve some problem of some particular size, then that is not a very useful measure because it may change tomorrow. It may change 5 years from now. So if I say that this program takes 5 seconds, then somebody will use the same program to run on the same input on a different machine, and it will take maybe 1 second. So it's not a good idea to compare. And for example, even in the same time, you write a program and you give it to me, and I have an average computer, it takes 10 seconds, and you run it on a very fast computer, it takes 1 second. How do we know that which one is the better representation of the actual time taken or required by the machine or the program? So what we have done, mathematicians and computer scientists in past knew that this could happen. So what they did, they said, okay, we will forget about time in terms of seconds or microseconds, and we will measure the time in terms of number of steps. So for example, if I have an algorithm, if I have a program that takes 100 steps to complete a task of a size n, then it will always take those 100 steps unless I change the program and the algorithm, right? So no matter when I implement it, no matter on what machine I implement and run it, it will always take the same number of steps. So the number of steps is now an independent measure of the time. Now, if I have to find out the exact time on a machine, then I will just figure it out on this particular machine, how much time it takes to run one step. If it takes 1 nanosecond, it's 100 nanoseconds in total for my program. If it takes 10 microseconds, then it is 1000 microseconds for my program. So I have an independent measure of time. So that's why we measure time complexity of programs, time complexity of algorithms, and time complexity of Turing machines in terms of the number of steps rather than the actual microseconds and milliseconds and nanoseconds and others. I hope this is clear. Is this clear?
Yes, sir.
Okay. So when we measure time of a program, of an algorithm, of a machine, we measure the time in terms of the number of steps. Okay. And when we measure the number of steps, we say that, okay, this becomes a function. Okay. So let me explain or make it a little bit more mathematical. So what is f of n? F of n is the maximum number of steps required by n, okay, to resolve or solve the input of size n, right? And we know that depending on the sigma, I can have so many input possible, right? So I have to just figure it out. किस input पे सबसे ज़्यादा time लगेगा. So it could be a very difficult task, but that's what we do. Okay? So it means that f of n is the maximum number of steps. So I may be very lucky. Let's suppose I have a string of size 100. Okay. And it's very easy to check whether this string is in the language or not in this particular case. Okay. मिसाल के तौर पे, I give you a very simple example. Suppose I have a number, let's say p. Okay. And I have to check if p is prime. Of course, this is a decision problem because a number p is prime or a number p is not prime. So the answer is yes or no. If I have to check whether the number is prime or not, it's a really difficult task. Why? Because I have to check whether this number is divisible by 2 or 3 or 5 or 7 or 11 or 13 and so on and so forth till p minus 1, right? So if p minus 1 is a prime number, fine. If it is not divisible by any prime less than p, then it means it is prime. Otherwise, it is not prime, right? So if p is very large, then I know that it will take a lot of time. Now compare this thing. Suppose I have a prime, suppose I have a number p with 100 digits. So 100 digit number is a really big number, right? And it will take some time before you could answer whether this number p is prime or not. Okay. But if I see this number is basically whatever this number is, suppose p is d1, d2. So these are the digits, right? d100. And I figure out that this last digit, the least significant digit, d100 is 0 or 2 or 4 or 6 or 8. Then I clearly know that this number is not a prime number, right? Why it is not prime number? Because this is an even number. And we know that no even number is prime except for 2. Since there are 100 digits in this number p, so this number is definitely not 2. And this number ends in 0, 2, 4, or 6. These are the even digits. So it means that this number is an even number. And I don't have to go and check all prime numbers less than p. And I can decide then and there that this number is not prime, right? Even though this number is huge, I can say that this number is not prime. But if the last digit is not 0 or 2 or 4 or 6 or 8, I don't have a direct way of figuring it out. And the easiest way is to check by all prime numbers less than p, right? Which is 2, 3, 5, 7, 11, and so on and so forth. 17 and 19 and things like that, right? So it means that it is possible to do a task in much fewer number of steps, even if the size of the input is too large, right? So for the same size input, our algorithm, our program, and our machine can take a lot of time or it can take less time. So that's why we say that this f of n is not just the number of steps. It is the maximum number of steps taken by the machine on any possible input of size n, right? Okay. And then we would come up with this notation. Okay. So I can say, suppose I have a Turing machine M, and I'm not sure what the language is. Suppose this is a deterministic Turing machine that stops on all possible inputs. And I say that the time complexity of this Turing machine is denoted or represented or captured by the function f, such that this f of n is 2n squared minus n plus 3. What does it mean? It means that this is the maximum number of steps required by this machine n on the input of size n. Okay? Okay? You get it?
Yes, sir.
Okay. Suppose I have another machine M2. Suppose this is f. I write this capital M as a subscript to show that this is the function f for the machine n. Suppose I have f n2 of n, which is 2n squared minus 2n plus 5. Okay, it's a different machine, Maybe on the same problem, but maybe a different problem, but whatever it is, now we have a different function. Okay, and so on and so forth. Is this in clear what we are doing? Okay. Now we will develop some notation to compare different functions. Okay. So for example, if I say that M is this and M2 is this, and suppose they are solving exactly the same problem, which machine is better? Which machine will take more steps? And which machine will take fewer steps? It may not be very clear from this example, right? But there should be some way of figuring it out. And that's why we have some notations that we will deal with. So I will cover one notation today and then the rest of the notations during our Thursday's class. Okay. So these notations are called O notations. I think you have covered these notations in your data structures class. But let us go through these notation one more time in a little bit mathematical rigorous fashion. And okay. So suppose I have a definition here. So we say that let f and g be functions. Okay. So we say that these f and g are functions from set of natural numbers to r plus. So what is this r? That is set of real number. And what is this plus? Plus means, so this r plus non-negative real numbers. Okay. Some people denote it like this. Non-negative. They don't say plus because if you put plus, it means positive. So they say it's a misuse of notation. So they come up with R, something like this. Okay. But whatever is the case, doesn't matter. So we mean that this R plus means non-negative numbers. Okay. We say this function f of n is in O of g of n. Okay. If positive integers c and n0 exist such that for every n greater than equal to n0, we have this function f of n is at most c times g of n. Okay, this is the definition. Okay, so outside this definition, now we have some usage. So we say that when f of n, we write equal, but this is not read as equal. Okay, it seems like f of n is equal to of. No, that's not how we read it. We read it as f of n is in. Okay, so let me write it. How it is read? It is read as f of n is in O of g of n. Is in read is in. Okay, so this thing is in. Or more precisely, some authors prefer this way: f of n is in O of g of n. Because on the one side we have a function, on the other side we have a set of function, a collection of a function, not a single function. That's why we cannot use equal sign. But equal sign is something that has been used classically, traditionally, historically. So we are not changing it. We will still use equal sign here, but this is not something that we will read as equal. We would read it as is in. Okay. So when f of n is in O of g of n, we say that g of n we say that G of n is an upper bound for f of n. Or more precisely that G of n is an asymptotic upper bound for f of n. To emphasize that we are expressing constant factors. Okay, so there is this constant factor here, right? So this is what we talk about upper bounds. So there's another definition which is about the lower bound, and there's another definition about something else. Most of these notations are mostly used in analysis of algorithms. But over here, we are content with this one definition. And maybe we will do one more definition, which is about the small o, right? So this is big O notation. So we say that f of n is in big O of g of n. And by this is what we mean, that whatever that we have on the right hand side that is inside the O notation is basically an upper bound, or precisely speaking, an asymptotic upper bound. Okay, so I think your calculus 1 information knowledge and discrete maths is combined here. So we are combining asymptotics and discrete maths. So later on we will see multiple different definitions, and some of those definitions will use limits. Okay. That you studied in your calculus 1. Any question?
No, sir.
Okay, is everything clear so far?
Yes, sir.
Okay, so I think we can stop at this point because there are not many students present, and we will continue from this point onwards on Thursday. Okay, I'm recording it, so I will upload the video on YouTube later tonight or maybe tomorrow. Okay,
Thank you, sir.
I will upload the recording, don't worry. Okay, thank you very much. Sorry for the situation that we are taking this class online, but this is the way things happen. So hopefully on Thursday we will be able to take the class in person on campus. Okay, see you. Thank you very much. See you on Thursday. Bye bye. Take care.